Good evening, ladies and gentlemen. My name is Ian Ritchie. I'm Vice President Business at the Royal Society of Edinburgh. I also happen to be a Fellow and Honorary Treasurer of the Royal Academy of Engineering. So it gives me great pleasure to welcome you tonight to the 22nd joint lecture co-hosted by the Royal Society of Edinburgh and the Royal Academy of Engineering. This lecture is used as an opportunity to engage members of the public who may not otherwise attend a scientific lecture and enthuse them about modern science and technology. First, a couple of words of welcome to the Royal Society of Edinburgh. We are the wholly independent academy formed to provide public benefit throughout Scotland. Since we were formed in the Enlightenment in 1783, we've drawn upon the considerable strengths and varied expertise of our fellows, of which there are currently more than 1,500. Unlike similar organisations in the rest of the UK, our fellowship includes people from a wide range of disciplines: science and technology, arts, humanity, social science, business and public affairs. This breadth of expertise makes us unique. Now, this actually also serves, I'm afraid, as an ordinary meeting of the Royal Society of Edinburgh. So there's about a minute's worth of business I'll have to do, and if you'll tolerate that for a few seconds. So this is an ordinary meeting of the Royal Society of Edinburgh. A minute of the last ordinary meeting is available and displayed in reception, along with a list of recently deceased fellows of the Society. Announcement of new fellows. Professors Mark Bradley and Gerald Buller acted as scrutineers for the ballot of election of new RAC fellows. They reported that over 40% of the fellowship voted in the ballot, and that all the names in the ballot list had been approved by at least 2/3 of those voting, as required by the Society's laws, and in fact all by a much greater level of support than that. The announcement of the election of the new Royal Society of Edinburgh Fellows has been released to the media on the 2nd of March, and a list of the new fellows is on display in the reception area. So that concludes the ordinary meeting of the Royal Society of Edinburgh. And it's now my pleasant duty to invite Professor Alan Miller to the stage to chair the lecture.
Thank you, Ian. This evening's lecture is the 22nd joint annual lecture co-hosted by the Royal Society of Edinburgh and the Royal Academy of Engineering. This lecture series provides an opportunity to enthuse the public about modern science and technology while providing an opportunity for engineers in Scotland to get together. This evening's speaker, David Miller, is the W.M. Keck Foundation Professor of Electrical Engineering and Professor of Applied Physics at Stanford University. He is co-director of the Stanford Photonics Research Centre. Born in Hamilton, David grew up in Banff and Perth, and he attended Perth Academy and then went on to St Andrews University, where he received a BSc in physics, and then his PhD, awarded in 1979, was from Heriot-Watt University, where he was a Carnegie Research Scholar. He was employed at Heriot-Watt as a research associate and then a lecturer in the Department of Physics before moving to AT&T Bell Laboratories in New Jersey in 1981 as a member of technical staff. From 1987 to 1996, he was a department head at Bell Labs, latterly of the Advanced Photonics Research Department. He moved to California and Stanford in 1996, where he served for 10 years as the director of Stanford's Ginston Laboratory and also director of the Solid State and Photonics Laboratory. With an H index of 70 from Web of Science and 85 on Google Scholar, David's spectacularly successful research career spans fundamental physics to the invention and development of new photonic devices. His research interests include optics and switching, interconnects, communications, computing, sensor systems, the physics and application of quantum well optics and optoelectronics, and nanophotonics in communications and information processing. He is a member of the National Academy of Sciences and of the National Academy of Engineering, a Fellow of the Royal Society of London, a Fellow of the Royal Society of Edinburgh, and the IEEE, the Optical Society of America, and the American Physical Society, and was awarded the honorary doctorate by the Free University of Brussels and as an honorary Doctor of Engineering from Heriot-Watt University. For his work on semiconductor nonlinear optics, quantum well optical properties, and novel devices, he was awarded the 1986 Adolph Lohm Medal of the Optical Society of America, was co-recipient of the 1988 R.W. Wood Medal, and received the 1991 prize of the International Commission for Optics. He was also an IEEE Lasers and Electro-Optics Society travelling lecturer in 1986-87 and was awarded the IEEE Third Millennium Medal in 2000. He has retained his links with Scotland and held the 2013 Carnegie Centenary Professorship, spending 3 months in Scotland, giving lectures and conducting collaborative research with the University of Strathclyde, Glasgow, St Andrews and Heriot-Watt. He is a highly valued member of the International Advisory Committee of the Scottish University's Physics Lines. We are delighted that David has travelled over from Stanford to give this joint RSE Royal Academy of Engineering lecture with the title Light, Energy and the Internet. I'm sure we're all in for a treat. I have known David for almost 40 years now, and I've heard him talk in many parts of the world, and he never ceases to provide a high-quality lecture. Of course, with the same name, and we have published together, there has in the past been some confusion between us, which I always encourage. It has never done me any harm at all. And as one colleague said to me, I remember some years ago, that I was A. Miller, but this is D. Miller. So I would like to invite D. Miller to the stage to give his lecture.
Well, thank you very much, Alan. We have indeed known one another for a very long time, more years than either of us care now to announce. But there's no relation, but thank you very much, Alan. So I'm very pleased to be here. I'm going to give you a talk which hopefully will be something for everyone. I may get into a few numbers and there might even be an equation in here, but it mostly will not be so heavy. And I think the story should be fairly clear no matter what level we want to do it at. And the title of this talk is Light, Energy, and the Internet. And the idea of putting energy in here with light might seem a little odd, but why that's in there will become clear as we go on here. So I'm at Stanford University. You saw my rather informal photograph, which is how I dress over there, but of course I always wear a suit and tie over here, as everyone does. All right, so first of all, I'd like to thank the organizers and the societies for inviting me over here. It's a great honor. It's a great pleasure to be here. I always like being back in Scotland, and I take as many opportunities as I can find in order to do that. And in particular, I'd like to thank Alan here and Stephen Lee for instigating this, and the societies for inviting me. What am I going to tell you? So this you already know. The internet is growing exponentially. Every year it seems to get bigger by some factor, and it changes our lives in ways that we just could never anticipate. Nearly all the information we send, over nearly all the distance we send it, is sent on light. And I think sometimes the man in the street is not aware of that. He has his cell phone, or perhaps he has an iPad or something else like that, and he thinks that wireless technology is the way that he or she sends all their information. But that's only for the very first part of the distance. For all of the rest of the distance, it's really sent on optical fibers. And it's the existence of optical fibers that actually has made the international internet possible. It basically has put the inter into internet. And I'll show you a little bit about that as we go forward here. Of course, electronics, that is silicon and silicon chips, that has been growing exponentially as well. And that's well known in something called Moore's Law, and I'll show you that if you're not familiar with it. But that law just celebrated, I think, its 50th anniversary. But the catch is that although the fiber has been growing very fast and allowing us to send more information, and the electronics has been growing very fast, allowing us to compute more information, the catch, and this is something that is kind of hidden again from the man in the street, is that down inside the machines that process information and that route the information to where it has to go on the internet, we're actually running into a substantial problem. It's at the junction between these two we run into a major problem. We are not able to keep up with our need to send information inside machines. And that may seem paradoxical, but even to run the internet, we actually need to send a lot of information inside machines, inside the routers that send the information where it has to go, inside the data centers that are run by the major corporations like Google that get us all that information that we've been looking for. Inside those machines, the connections are not keeping up. And that is actually starting to impact what we can do on the internet. So there's two ways in which it's not keeping up. We're actually running out of space for wires. And we call the wires inside the machine interconnects, as just a way of characterizing them. So we've run into a problem with what you could call interconnect density, and we're running out of energy. Most of the energy in information processing is actually spent on sending the information about inside the machines, inside the chips. It's not actually spent on sending it the long distances. That might seem paradoxical, but it turns out to be the case. And it's mostly because we need to send a lot more information about locally in order to get the really specific information out over the long distances. So when you put a query into your search engine, there's a lot of work goes on inside the data center to sort everything out. That takes a lot of connections inside that machine. Then that information, much distilled, then heads off to your computer. And we're running out of that energy, and I'll show you that. Now, the good news is that new kinds of optical technology may provide us a solution for that. The optics may provide the solution inside the machines that allows us to send more information inside the machines at higher density and lower energy. That might seem an obscure thing, but if we don't solve those problems, we will not be able to keep on scaling up the internet and everything that brings us. This is exciting, but the technological challenges are significant. They're going to take major investment, but there are lots of opportunities. And to a person like myself who works in research, there are many opportunities out there for new kinds of devices, new kinds of technologies. It's really a remarkable sandbox for somebody like me to play in, but there's a real point to it because there's a real problem we have to solve. So let me take you back a little to 1865. And in 1865, there was a gentleman by the name of William Thomson, subsequently known as Lord Kelvin or Baron Kelvin of Largs. And William Thomson was a very good scientist. So he had a major influence on the development of what we call thermodynamics and also of electricity and magnetism. He was an outstanding scientist in his own right by the time this particular problem came along. At this time, in the late 1850s and on towards this particular date here, people were installing more and more telegraph cable. It was a very important thing to have. The empire needed it in order to run the empire. And the empire, the British Empire, subsidized many of the telegraph lines because they knew it was very important to be able to get that command and control out to distant parts of the empire. And that technology had been getting better. But then came the really tough job of saying, well, now let's try to send this many thousands of miles, for example, under the Atlantic, so we can connect North America to Europe. Well, there was an attempt to do that, and there was a gentleman who was really pushing it, and we'll miss his name out because it doesn't show him in such a good light. And he thought he knew what he was doing, and they had laid some submarine cables already, under the water from England to France, for example, but that's only a few tens of miles. Now we're talking thousands of miles. And he thought, well, they could do this, so they raised the money and they set out to do it. And Thomson said, but wait a minute, do you understand how the signals actually go over those wires? So he looked at the mathematics and the physical modeling. He did the first actual modeling of what we would now call interconnects as to how signals would be sent over very long wires like this. And he said, it's going to be difficult to get this to work for the following reasons, and maybe you should redesign the cable this way and so on. Well, the person who was laying the cable didn't want to pay any attention to him and set off to lay the cable, and it was a disaster, and it didn't work. And finally, he couldn't get enough signal at the end of the cable, so he ended up eventually sending 2,000 volts of signal down the cable, and he blew it up. And Kelvin said, look, we can sort this, but we need to make some changes. And Kelvin, being a very, very good scientist, got in there and became a very, very good engineer. And it was a major triumph. the details of which were due to Kelvin from a technical point of view, that they got this transatlantic cable to work in 1865. And it worked using an instrument that Kelvin had invented, a galvanometer, a mirror galvanometer that could detect the very weak signals at the end of the cable so that people could actually see what was going on. And the person who had installed the cable for some time pretended that it wasn't Thomson's device that was at the end of the cable, it was his device, but it wasn't, it was Thomson's. So this is an instance of a scientist turning into a very good engineer. And here's a picture from the time of a map of this submarine telegraph line here going from Ireland over to Newfoundland. This is actually the very first attempt to lay it, but the subsequent ones went basically the same route. And here's what the cable looks like. And this is several inches here. This is very heavily armored cable. This is what you have near to the shore, and it's still true today that when we lay these cables, they're kind of like that. And this is a somewhat lighter weight casing that's used for some of the longer runs of the cable. So that's from 1865. You can actually see it on here. It says Atlantic Cable 1865 down here. Now, this was a tremendous industry, and it moved ahead very rapidly, and very large amounts of telegraph cable were installed. And it's so much so that, in fact, they nearly caused an ecological disaster. And the ecological disaster they nearly caused was the almost complete extinction of gutta percha trees, which were used to extract the insulation. There's a natural latex in those trees. They extracted the insulation to put inside the cables, and suddenly they discovered towards the end of the 19th century they were completely running out of this, and the forests had been completely decimated. It was a near catastrophe, one of the earlier environmental problems of the Victorian era. Anyway, they solved that actually by having a more efficient way of extracting the latex. And modern cables, of course, are insulated with artificial plastics like polyethylene. But anyway, this is a great thing, but there was one particular thing the empire wanted to have. It wanted to have what they call a red line that went all the way around the globe, only touching upon British territories, or what we now call Commonwealth countries. And the one particularly difficult link, and this is from Vancouver Island, down to a small island that was British territory, Fanning Island, in the middle of the Pacific Ocean. And this was the longest single run. This was 4,000 miles. And they did manage to get it to work, but you can't get much information down it. And you can get about 100 characters a minute, and for those of you used to modern units, that's about 7 bits per second. So the bits are the on and offs that we use for digital information. And just by contrast, the modern submarine optical cables are running approximately a million times faster than that. So 7 bits per second. And actually, what you have to do is you have to read this funny squiggly signal here, which is produced by a siphon recorder, or what we might call a strip chart recorder, a little pen that wiggles as the paper is dragged through it. And that was also invented by William Thomson, Lord Kelvin. He invented the siphon recorder. And the operators had to look at this and try to decipher it as Morse code. And one of the problems is that on a very long cable like this, it's got a lot of resistance and a lot of what we call capacitance. And that means it takes a time to charge up. You put a voltage at this end, it takes quite a long time for it gradually to develop at that end. So if you turn on and off the signals too fast at this end, you just get a smudged out mess at that end. And in fact, these operators got very good, and those of you who are into signal processing, these operators were performing signal processing to deconvolve the signal from this squiggly line here. And they could operate past the point where you would think you might be able to decipher it. They learned to do signal processing in their heads. Anyway, that was the single longest link. It did work, but very low bit rate, as we would call it, along here. And of course, we did keep laying more and more electrical cables, and the key to get more bit rate on them is you have to bury amplifiers along the way. And that takes more effort, but that did grow quite substantially. But nowadays, we don't do that at all. Nowadays, we use glass fibers, and the glass fibers we use are bits of glass that are approximately the same thickness as a human hair. And these glass fibers have got so little loss that it's only a factor of 10 loss over 50 kilometers. So think of looking through a piece of glass that is 50 kilometers long, and you can still see through to the other end of it. 10% transmission, but that's enough. It's phenomenally transparent. It's a remarkable technological achievement. And that means, so first of all, these glass fibers have got less loss, less attenuation, less of this factor of loss here, and also less of this so-called inter-symbol interference, this smooshing together of the signals that we got down the electrical cable. And that technology was introduced starting in the 1980s, and now it's completely dominant for all long-distance telecommunications. So here's a map of the submarine cables that we have today, and these lines get kind of fat, and the reason why these lines get kind of fat is because the capacity of the cables kept going up, and the artist drawing the map needed to have some way of indicating that. But he could only indicate that in a logarithmic sense, because the early cables were sending hundreds of millions of bits per second, and the new ones are sending 10 times a million bits per second down a cable. It's a massive increase. They're not just on one fiber, there's bunches of fibers inside the cable, but these are sort of 5 terabit per second cables compared to the 100 megabit per second cables that were installed early on. And this is what enables us to do the internet across the globe. And if you look inside Europe in a little bit more detail, here are just the submarine cables. These ones are actually submarine cables as well, under the water. Here's the submarine cables within Europe. And then just got a map here from the United States. These are the other cables of just one of the network suppliers in the United States. This is level 3 communications, showing their sort of backbone network. And there's lots and lots of network suppliers, and each of them has got their own networks. We're laced with optical fibers, and this is what is carrying all our information. Now, let me just give you some numbers to give you a sense of the growth of the internet that is in many ways enabled by this fiber. And I'll just use some numbers for YouTube. Has anyone in the audience heard of YouTube? All right, has anyone not heard of YouTube? Okay. So YouTube, there are over 1 billion different users access YouTube each month. So a large chunk of the world's population. The number of hours that people are watching on YouTube each month is up by 50% compared to the same month the previous year. 60% of a creator's views, if you put something up there, 60% of the views come from outside your home country. And if you thought you were not able to keep up with YouTube, you're perfectly correct. There are 300 hours of video uploaded every minute to YouTube. And over the past year, I have contributed to this. I got into generating one of these online courses. Have you heard of these massive open online courses? So I've been doing one on, wait for it, quantum mechanics. So if you've been having difficulty sleeping, you can log on to my class. But I'm an example of this. I've uploaded about 50 hours of video, and I can attest that this stuff is, in my case, 70% of the people who look at it are outside the United States. And it's viewed by people in 111 different countries. It gives you a sense of the impact of the internet. You wouldn't believe there are people in all these countries who might want to learn about quantum mechanics, but apparently it's true. Some other fun facts about the internet and telecommunications generally. There are now almost 7 billion mobile or cellular subscriptions worldwide, and that's about 4.5 billion unique users. So yes, 63% of all humans have a cell phone. And there are more phone connections than there are people in the world, and there are people in this room who say, oh yeah, I do have 2 phones, and I've got that iPad, and I've got that other thing. And it's actually true that many people in the developed world, of course, have got more than one such device. But even accounting for that, 63% of the world has got cell phones. And almost 3 billion people, about 40% of the world's population, are using the internet. So it has achieved remarkable penetration. And some numbers, if you don't like these numbers, then don't worry too much about it, but this particular field gets you using prefixes you had never seen before. So you might be used to milli and kilo and things like that. Well, this one goes all the way up to zeta, and I don't think there's one after that, or zettabytes. That's 10 to the power 21 bytes, so 21 zeros in there. We are going to pass this particular threshold for the amount of information we send in a year. Now, that may not mean too much to you, but that is 250 million bits per second is flowing over the internet today. That's roughly what that means. And the rate of growth of what's called internet protocol traffic, IP traffic, that's increased by more than 5-fold in the past 5 years. And it's estimated that between 2005 and 2018, it will have grown by a factor of 64. we're looking at an enormous rate of growth of the amount of information we are sending over the internet. And bear in mind that although there are 40% of the people in the world on the internet, very few of those have got broadband internet. So there's a tremendous capacity for growth just within people. And then you may have heard the term Internet of Things. We're moving into the era when your toaster will be talking to your refrigerator. We're moving into that era where most of the connections will actually be machine to machine of some kind. Now, the fiber technology is one of the key things that has enabled this. And this is a graph here showing the capacity, that is in bits per second, of optical fiber starting from their early deployment back here in the early 1980s. So this is about 100 million bits per second. And then up here, we're at this region up here is about 100 million bits per second. And various technological things have happened along the way to keep this growing. But the capacity of just one thin hair-like fiber is truly enormous. And we are not running out of space to lay fibers in the ground. There is tons of space to lay fibers in the ground. It's not like the road system. We basically run out of space for the road system. We have not close to run out of space for optical fibers because it's just these thin little hairs. And yes, if you've been looking at the numbers, it is probably just about possible that you could put the whole internet on one fiber. If all the traffic happened to be going from one place to another, you could actually, just at this instant, still just about squeeze it onto one optical fiber. The capacity of optical fibers is truly enormous. So the long-distance information problem, but that itself is not really a major problem. If we didn't do anything to the technology now, we would, at least at linear cost, be able to keep on increasing the capacity of the long-distance transmission network as a transmission network. What about electronics? What has been happening with electronics? Well, there's some fun facts about electronics. It is the most complicated thing that we design and make. And according to Gordon Moore, who was one of the progenitors of the whole field, one of the people who started Intel, he calculated that even in the early 1990s, that there were more transistors made each year than there are raindrops fall in California. Now, the weather in California is nice, but that's not the point. And there's something like 10 to the power 18 transistors made each year. That's probably more than existed at the beginning of a year. So if you took all the transistors that had been made up to that point, you probably make about the same amount each year as everything you ever made from the dawn of history. And it's approximately 10 to 100 times the number of ants on the face of the Earth. So we're making a lot of transistors. Now, the ants are a bit smarter, but we may be getting there, you know, a little bit of good circuitry. Now, it's also easy to do this calculation. We use lithography, very fine patterning to make the integrated circuits. And the number of devices that we're making today, actually, we're able to make roughly a billion, or American billion, 1,000 million devices or so on actual chips that are sold. It's easy to show that that's enough, more than enough, to print an entire book on a little chip that is the size of your thumbnail. In fact, we passed that point quite a long time ago. So you could print an entire book on your thumbnail. Now you could probably print an entire encyclopedia of books, more than that, on your thumbnail. That's the level of complexity we are able to etch into silicon chips to make them today. And it's also true, this is a subtle point, if you've been looking at what's happening with electronics, and if you're a bit into the details of it, you might have noticed these things called clock rates. It's how fast you run the transistors. And that for many years was increasing with every generation. It has actually leveled off, and there's a good reason why it's leveled off. But it's not because the transistors aren't fast. The transistors themselves are actually very fast. And I use this pico prefix a lot, that's a millionth. And the transistors are actually extremely fast, but we don't run them that fast, and there's a reason for that I'll come to. But this is Moore's law. Gordon Moore predicted in the early 1960s that the number of transistors that you could put onto a silicon chip would double every 18 months or 2 years, something like that. And that has actually held up very well, and we're now at about the 50th anniversary of that law. And I put this graph together a little while ago, and I thought I'd go in and update it, but it turns out it's right. I didn't have to update it. And right at this point here, we're currently making chips with indeed about 1 or 2 billion transistors on them, which is what this would be here. So that's exactly where we are. The problem with chips is actually not making more transistors. It's that we don't have enough power to run them, or that we can't sink the heat that they generate off the chips. And we also can't wire them up. So if you look at the performance of silicon integrated circuits in actual machines, their main bottleneck is not the speed of the transistors, it's the speed of being able to connect in and out of the memory to get the data that they want to operate on and get it back in and out of the memory. That's actually the bottleneck. And that's down to this wiring density problem. This is a collection of data, a very good collection of data put together by Hilbert and Lopez, and they published it in Science, and I extracted some of their numbers out of there to construct this graph here. This line here is the total amount of telecommunications traffic we had, and back here in the 80s, it was mostly phone lines. And that did keep on going up a little bit, but what happened round about the year 2000 was that the internet traffic, the data traffic, took over. And it was increasing at a much greater rate. And this particular rate in here, this dashed line, that's about a factor of 110 years. Now, it may be slowing down a little bit from that now, partly for the reasons I'll discuss, but it is growing very fast, and also the number of transistors that you could put on a chip and multiplied by the speed at which you could run them meant that this measure here of how much installed compute power we had was also increasing at the same rate. So these two were increasing at something like a factor of 100 every 10 years. But what was not keeping up was the connections between them, was the connections inside the machines. That's where the real problem lies. And if you look at these kinds of rate of growth, you have a massive problem keeping up with that. And we're running into these two issues here of energy and communications density. I'll talk about the communications density one first, actually, but I'll just mention this. I'll come back to this number. At the present time, we're using somewhere between about 5 and 10% of our electricity to run all of our information, communications, and processing systems. And that has been growing steadily. So I'll come back to that. I'll talk a little bit about the density here, maybe show you some pictures. The core problem is the following. That if you had, suppose you had a wire here, so I've shown it as, an imaginary copper wire, maybe above a plane here, it doesn't really matter, the precise design of the wire. If you take this wire and say, well, I'm going to turn on a voltage at one end and look to see how long it takes the voltage basically to appear at the other. Well, if you shrink this whole wire down in all three dimensions, it turns out that time does not change. So the number of on-off keys you can do here and pick them up at that end turns out to be the same for this wire as it is for that wire. And that's the problem. As you shrink the whole system down, you can't get any more information through it. It's what we call a scale invariant result. So you could write it down as an equation here, but the point is that once you have filled all the space with wiring, you can't get any more information down the wiring. You could try to miniaturize the system, you don't get any more information down. You could try to make it bigger, you don't get any more information down. You reach a sudden wall where you just can't get any more information through the wires. And you can do some very fancy things called modem techniques to try to improve that, but you're starting to climb a cost and actually more energy dissipation curve if you're going to try to deal with that. Now, optics does not have this problem, because this problem comes from the resistance, the electrical resistance of copper and other metals. And optics completely avoids that because it doesn't have resistive loss. So let's look at some wiring density pictures. This is a wiring density picture in Broadway in New York in approximately about 1870-something, 1880 or so. And you see you've got lots of these telegraph wires here. And down at the bottom you have the information processing units, these little people down here. They're the things that do the thinking. Bear in mind the scale of this, because this is roughly, we retain this. And basically the entire volume of Broadway here in New York is filled with wires. This is a telephone exchange in the early 1970s, and basically it's got the same problem. The entire space between the racks of switches is filled with wires, in this case so-called twisted pairs. This is rather frightening. I've never been able to find out where this is a picture of, but these are what are called Cat5 Ethernet cables, so if any of you plugged Ethernet cables into your computers, that's what these are, and this is a most horrendous looking mess. And that's the surface of a chip, a silicon chip, if you take all of the other stuff out and just leave the metal so you can look at it. It's really got the same problem, and you can see that if you look in cross-section at a silicon chip. So this is in 2005 here. This is the people down at the bottom. The transistors are down here. Actually, you can't even see them. And then these are all the levels of wiring. And as you go further up here, they make the wires bigger because these ones are going to carry the signals over longer distances. And this is what it looks like, again, in a sort of plan view. That was 2005, 7 levels of metal. This is the latest chip. This is an Intel chip, the one that if you buy what's called a CorrFRSE processor, this is the technology it's using. And it's what's called a 14 nanometer process. Now, there's a scale bar on here. This is a top view of all the transistors. And this scale bar is 699 nanometers. That's about 70% of a micron, and your human hair is of the order of 100 microns. So this is less than 100th of the size of a human hair is this distance here. This is a picture of these field effect transistors, as they're called. The unit here is nanometers, so they're thousandths of a micron, and a micron is millionths of a meter. And the current level of technology we're at least called 14 nanometers, which is a very, very small size. This is the cross-section of that chip. So this is looking down at the top, looking down at the transistors. These are so-called FinFETs in here. And this is a cross-section. You can't see the transistors. They're just down here in that layer. And if you can see them, these little vertical bars in here are these vertical bars. And then in this chip, there are 13 levels of wiring. So it's not so far from the scale of the little human beings down the bottom here on Broadway and all of the wires filling up all the space between the tall buildings on either side. It really hasn't changed very much from that, what you could call aspect ratio. Now, this leads to a problem, and it's called, rather unromantically, the byte per flop gap. So flop is a measure of a calculation that you can do in a chip. It's called a floating point operation per second, or it would be flops. So it basically measures, how many of those calculations can you do, how many additions or multiplications can you do per second. So you can characterize a chip by how many of those it can do. So the march of silicon, this Moore's law, is this orange line here. It goes up in somewhat kind of jumps. But this is a prediction of what would happen with the number of flops, the number of calculations you could do. And then this dashed line here is the attempt to see how much information you could get off the chip. And eventually, these part company. The ability to get information off the chip cannot keep up with the ability of the chip to do computations. And what you would like to do with a computer is to be able to get 1 byte, that's 8 bits of information from your memory so you can do something with it, then add it up or multiply it, a flop of some kind. So you would like 1 byte per flop. That would be a nice point to be in a computer architecture. And we basically are losing that ability. In fact, we've lost it some time ago, and the gap is getting wider. So the ability to get the information to do anything with is not keeping up with the ability to do stuff with it. It's like we've got an office building full of people who are just sitting twiddling their thumbs because the mail system's not working. That's basically the situation we're in, and it's getting worse. And more graphs here, a bit more technical, but these are some actual plotted data for the chips that do the graphics processing inside your computer. So you typically have more than 1 chip inside your computer, one that does your word processing for you or whatever, and another one that drives the display. And the one that drives the display is actually the one that really does a lot of calculations. And one of my colleagues at Stanford, Bill Daly, is the chief technical officer for this company, NVIDIA, which probably has made the graphics processing chip that sits inside your computer. And this was a state-of-the-art chip in 2011. Now, I'll tell you something about these numbers here, but the key point to note is that these lines are steep, and these are basically the ability of the chip to do floating point operations. So they're the ones on this axis. And this is the ability to get in and out of memory to get the information to do the calculations on. It's just not keeping up. And there are several other points here. This is a kind of geeky graph with lots of different numbers on it. But one of the points is the following. This chip runs at 1.6 gigahertz. What should we take from that? Well, that's more or less the same speed we've been running computers for the last decade or so. That has not gone up. Why has it not gone up? It's not gone up because if you run transistors faster, you need to run them at slightly higher voltage. And if you run them at higher voltage, you dissipate a bit more energy for everything you get the transistor to do. And it turns out these chips are not limited by the speed of the transistors. They're limited by the energy per operation. They're limited by power dissipation. And this chip is pretty much, it's a high-performance chip, 130 watts. It's kind of, you could fry an egg on that. kind of temperatures that you can get to with these things if you're not careful. That's pretty much as much power as you can get off a chip. So this thing is run at 1.6 gigahertz, so they run the transistors so they take the least amount of energy. These chips are already energy limited. They're not speed limited by the transistors. The transistors could run way faster than this, but you couldn't sink the power from them if they did. Now, this thing does a lot of work here. These numbers here, 665 gigaflops, that's a lot. But here's a very interesting number. Even with this memory bandwidth, if you run this chip full bore and try to get it to communicate as much as it possibly can, it spits out this amount of information per second, or in terabits per second, 1.4 terabits per second. That's off one chip. The entire long-distance internet traffic in 2015 is probably 250 terabits per second. So one chip is close to putting out 0.5% of the entire bandwidth that can go over the internet. And this gives you a hint as to what the problem is. We have to send vastly more information around inside machines than we have to send between machines. So although it might take a moderate amount of energy to send things over a long distance, we have to do so many more pieces of communication inside the machine that that energy, that power, turns out to dominate, even though those shorter distances don't take as much energy. Could we do this optically? Well, yes, we certainly could imagine in terms of density. We could imagine laying optical fibers, these kind of hair-like objects, side by side around our chip. And with a bit of work, we could actually get all the information on and off those. We would have to do some work. We would have to actually run them pretty fast, and we'd need to use multiple different colors of light down the fibers. But we could actually, even out here in 2023 or whatever, on this particular projection, we could actually just keep up there. It's a little easier if, in terms of keeping up, if we were to take the information in and out the surface of the chip, and we can run through some numbers, but the details don't matter. But if we bring the information in and out the surface of the chip, we turn out we've got plenty of space to do it. But that's a much more radical thing to do, and having the information flowing through free space tends to freak out electrical designers. They think you can't do that. Actually, we do this all the time. My glasses, for example, are looking at some millions of pixels, which is what enables me to see you and you to see me. So we're kind of used to that. But this optics would be somewhat different. It would be a different kind of system. But it looks like the optics, one way or the other, could handle the density of information. What about the energy? Well, let's go back and look at the total energy involved in running the internet and all of our information processing. And this is a very good study here. And the key takeaway point here is that these numbers are telling us that in 2012, about 4.5% of all our energy was used to run all of this information processing, or electrical energy. And that's not including actually your cell phones, and it's not including the TVs. And if you put those in as well, it probably comes to about 9%. Now, you might think, well, 9% is not so bad of all our electricity, but the problem is this is growing faster than our ability to generate electricity. And then on top of that, remember, we're trying to ramp up the amount of information we send over the internet by somewhere between, on the low end, a factor of 10 every decade, and on the high end, a factor of 100 every decade. So if we don't do anything to reduce the energy we require to run machines per operation, we're not going to be able to keep on scaling up the internet, because we would use all the electrical power that was there. And we can't do that because we need it for other things, like lighting and all sorts of other things we do with it. So there's a real energy problem here. And incidentally, note it's actually the network energy that's increasing fastest in this particular illustration here. But those are the numbers to bear in mind. Somewhere between about 5 and 10% of all our electricity today is used to run our information technology. It used to be it didn't matter. It was completely negligible. But now that is not true. And if we're going to keep on scaling up the internet, we're going to run into a real energy crunch. So I'll show you some numbers here. And again, if you're not used to units, don't worry, but it goes from high energies to low energies from top to bottom here. So to run your cell phone, to send a bit of information in and out of your cell phone over to the cell tower, takes about 10 millionths of a joule. And that's actually the highest energy to send any bit anywhere. It's your wireless devices. They're the most energy expensive. That's why your cell phone gets hot sometimes. That's the thing that takes the most energy per bit. Very fortunately, it's not very far before that wireless energy gets put into, first of all, electrical cables and then pretty quickly into optical fibers. And that gets the further transmission energy down. But your wireless device is actually the most energy expensive part of the whole story. Sending a bit over the internet itself maybe takes about a tenth of that. So it takes 10 microjoules to get from your cell phone to the cell tower. And it takes 1 microjoule for it to get wherever it's trying to go before it goes back to another cell phone at the other end. And in fact, that's dominated by the fact that inside your home, you've got a 10-watt dissipating box sitting on your wall that is plugged into the network. Once you start running more information through that box, and if you manage to keep it just dissipating 10 watts, then that energy starts to disappear per bit. And then it turns out the dominant energy is actually inside the machines, the telephone exchanges of the internet, that are routing your information. You come in a fiber from Chicago and it routes it out to New York, or you come in a fiber from Edinburgh and it routes it out to Aberdeen or something. Those machines are actually where the dissipation is in the routing and sending stuff over the internet. And that, if we got rid of this so-called fixed power of the 10-watt box on your wall, that would be about a fifth of this, 200 nanojoules, 200 billionths of a joule, for an entire routing. But ironically, it's the energy inside the switching machines, not the long-distance transmission energy. And the actual links themselves for over the internet only take about 10 nanojoules, so a 20th of that energy. So most of the energy is actually inside the switching networks, the telephone exchanges of the internet. As you go down to shorter distances, we go inside a machine. One of the things we need to do is pull information from memory. We need to go to the filing cabinet and get stuff and bring it back. That takes a number, this is 30 trillionths of a joule. That might not sound very much, and this is again from my colleague Bill Daly, who's Chief Technical Officer of NVIDIA. Communicating just a bit off a chip maybe takes about tens of these, or rather comparable to that. The floating point operation itself, the actual calculation for every bit, only takes about 1 of these picojoules. The energy stored inside the DRAM cell itself, you need to store energy in this cell so it can retain the information, that's only about 10 femtojoules. Now, femtojoule is a thousandth of a picojoule. So a hundredth of that energy there. And once you come down to an actual logic gate, to perform an actual logic operation takes less than 1 femtojoule. That's a thousandth of this energy, or 10,000th of that energy. And if you come all the way down to imagining you could make a device that would switch with 1 electron or 1 photon, you go down another factor of about 10,000. So the fundamental energies that we need in order to store a bit of information, in order to perform one logical operation, they're not so high. The real energies are in communicating the information in and out of even the chip, or even within the chip. I'll give you some numbers here. This is for fun. So on chips today, we're probably up to dissipating about 80% of the power just to send the information around on and off the chip and inside the chip. It costs as much to power a server, that's one of the computers that sits inside a data center. It costs as much to power it over its lifetime as it costs to buy it. So the companies like Google, for many, many different reasons, are very aware of power dissipation, and they do a very good job of engineering that out as much as they can. They are really aware of that. The system power is environmentally significant, so I gave you these numbers. And remember, this is the 4.6% maybe today. Internet traffic, as I said, has been growing by at least 100 per decade in the early part of this century. It may be slowing down a bit to 25 per decade. But remember, if I didn't do anything about the efficiency with which I handled that information, I would rapidly run out of energy to do anything whatsoever. So it's very clear I have to do something about energy. Now, here's a question for you, and those of you who are into numbers here might know this one. But I'll put it in another way. How much energy does it take you to do a Google search? So you type in your favorite star or football player, whatever, chef, I don't know what you like, into there, and you're just about to hit enter. How much energy does it take to do that? Now, you may not know the numbers here, so let me ask it this way around. How many times would you have to do that before you would have dissipated enough energy in the internet to boil the water for your coffee? So you're going to click this thing. I mean, do I click it once, that boils the water, or I have to click it 1,000,000 times to dissipate enough energy in some distant data center to boil the water? Anybody get any ideas?
10,000.
All right, we've got a 10,000 here. One person says 10,000, very brave. I've got any advance in that, smaller or lot? Sorry?
50,000.
50,000. So we think I have to click this thing 50,000 times. Any advance in 50,000? The answer is 70. It takes about a kilojoule if you hit enter, and 70 kilojoules will boil a small cup of water, raise it up to the temperature you need to make a cup of coffee. It's way more energy than people think. They usually think that energy is negligible, but it's quite a lot. However, it's also true that it's the same energy as your computer dissipates when you sit there looking at the screen for 10 seconds or something like that. It's not so different from those numbers. But the internet is not free in terms of energy dissipation. And here's another one. Even the interconnect power just within servers to run the internet is a vastly larger amount of energy than the energy we generate by solar photovoltaics. So this is at least as environmentally important a problem as solar energy. And the energy that you never even burn is the most environmentally friendly of the whole lot. It doesn't mean we shouldn't work on solar. We should work on solar. But this is an environmentally significant problem. This is the inside of a Google data center. So you see lots and lots of rows of racks here. And this is, you're looking along a rack, and every one of these sort of bricks here is a server. It's a little computer. And this is the cooling water system underneath it. And that is not a miniaturized bike. That's not a child's bike. That's an actual adult's bike there. And these are the pipes that carry the cooling water. And if you don't think this is dissipating any energy, here are the cooling towers. There's serious energy dissipated in the internet today. And these data centers are actually among the more efficient ones. These big ones done by the big companies are rather efficient data centers. There's all sorts of other ones run by specific entities that are nothing like as efficient. But there's real power being dissipated here. There's real steam coming out of these things. How much energy would we have to do interconnects? Well, again, a few numbers here. If we really tried to keep up with just what a chip wanted to do, we'd need to get down to these kinds of numbers, basically 100 femtojoules, a tenth of a picojoule, if we were to keep up in later years. And that's pretty hard going. And here's the problem, and I apologize for throwing an equation in here. When you're running a wire, as I said, you turn on a voltage at one end, you connect it to a battery, and you want a voltage to appear at the other end. Well, that involves charging the wire up. So you're going to end up with a volt across the whole wire. That's got energy stored in the capacitance of the wire. And you end up having to throw all that energy away. And we can calculate that energy, and it turns out that it almost doesn't matter what kind of wire you're looking at. The answer comes out the same per unit length. And the specific numbers here and the specific details don't matter too much. But basically, if you're trying to send a signal over the width of your thumb, with just turning on and off a voltage of the typical voltages you have on chips, so this would go from one side of the chip to the other, the answer to that is something in the scale of a picojoule to charge and discharge that wire. And there's nothing you can do about that if you stick with that voltage to send the signal down the wire. You can't really make low capacitance wires. It turns out that's not really possible. And this is the source of the energy dissipation in information processing, is charging and discharging wires. And just to emphasize that point, here's a schematic of some logic gate with nice little symbols we use for transistors. And here's a wire going from one side of the chip to of the logic gate to the other. Now, these things are really, really tiny now. These are much smaller than a micron. But it doesn't matter what size they are. It turns out the energy required to turn this gate on and off is about the same as the energy to charge up the wire that goes from one side of it to the other. So at the level of the things that are making the decisions, the energy required to make the decision and the energy required to communicate it just one gate further over are roughly the same. So that means that even, from gate to gate, the energies are about the same, but usually we have to send the information further than that, so we have to spend more energy. So this is a simple proof that the majority of the energy is actually spent in sending the information around, and it's mostly spent in charging and discharging wires. Well, how does optics help with this? One of the keys is a thing called the photoelectric effect, and that was discovered in the 1870s by Heinrich Hertz. And he didn't know what it was, and it took Einstein to sort it out. But the bottom line is, with light, you don't have to charge the wire. There's no wire to charge, and you end up working with photons at the end of the wires here. And that solves this problem, not having to charge the wire. And that's what we'd like to get to with optics. Well, let me move ahead here. I've been enjoying myself too much, so we'll flick through some more pictures. So the question is, are we going to be able to do this all the way down to the chip? Can we keep on pushing, not just for these long-distance communications, where optics is basically already won for all of these? Can we keep on pushing down inside the systems, even into the chip? And we can look at this idea of interconnects within machines, and I'm just repeating the argument I've already put up. We need to come up with something that reduces the energy per operation inside the machine, improves the density. And the key point is, there's really no other physical solution other than optics. There's nothing else waiting in the wings. If we don't manage to do it with optics, we don't manage to do it. And we can't use the technology we were using before, because it takes too much energy and it wasn't meant to run at these densities. So let me skip through most of this one here to save some time. Can we use silicon itself? Well, that's a very interesting question. So this is a serious attempt now to get silicon to do the optics. And these are tiny little waveguides on the surface of a silicon chip that are in fact carrying light about inside the silicon. And this is a mock-up by IBM. This is an actual picture. This is a mock-up of the idea of light beams running in and out of the silicon. And they've been making these chips now. This is 2010, these pictures, but this is actual technology from 2013. Intel is also looking at it. They did some prototypes in 2010. And there are ways in which you could do a little bit better with the silicon. The silicon is not very good at influencing light, but there are ways of making tiny little what they call ring resonators to make that a bit better, but these are somewhat tricky to work with. There are other approaches. You can add germanium into silicon processes. It's a similar enough material, and germanium can do things that silicon can't. You can modulate light quite easily with germanium. You turn on enough voltages on it, and that's what these devices are. You can change the transmission of a light beam through the germanium, so that's another future possibility. And you can start to use really, really tiny structures. This is possibly the world's smallest radio antenna. And this here is about 320 nanometers long, so much, much less than a micron. And it's taking light and putting light into a detector as if it was a radio antenna. And with the nanotechnology we have these days, we can start to look at these ideas. To give you a sense of it, here's a chip. This is a thing that's about the size of your thumb. And if we start focusing down inside here, keep on focusing down inside, eventually we get down to here, which is where we're making that little antenna. And here's the picture of that antenna. It's approximately the same size as one logic gate on the chip. And we can guide light around as if they were like electrical circuits. We can do that with little pieces of metal. We can guide light around like pairs of wires. We can do that at very short length scales. And we can start to play with what we call nanophotonic structures, where we pattern the silicon using the tools we made for electronics, but to make very complicated optical structures. And this is kind of like an optical pinball machine. But it does this magical thing that it can take these different shapes of beams at the input and spit them out different output waveguides. And the funny thing about this is we've no idea how it works. We have absolutely no idea how it works. It's true. We can design it, but it's completely blind. This is something one of my colleagues at Stanford designed. It's a beautifully complicated little structure here, and it does the same kind of trick. It separates out different shapes of light beams and puts them at different outputs. And this is the level of complexity people are looking at now in optics. This is work from Mike Watts at MIT. These are tiny little grating antennas. They will spit out little light beams. And about 20 of these is the size of an optical fiber. So the optical fiber is bigger than my slide here. That would be the scale of an optical fiber. So we're starting to be able to do some really cool things exploiting silicon technology. We're starting to figure out how to make self-stabilizing systems by exploiting the combination of optics and electronics, using little electronic feedback loops to keep everything sort of lined up, even in very complicated systems. So we're having a lot of fun with that, and we're having a lot of fun with trying to exploit the nanotechnology to make smaller, lower energy devices, and there's a lot of potential there. So in conclusion, I hope I've shown you that optics is a key to enabling our modern information networks. If we didn't have optics, they just wouldn't be there. We have severe problems inside the machines that we need to fix, of density and energy of sending information inside the machines. Optics, as I said, is the only known solution to this, but we need new technologies in order to do it. It takes money, it takes time to develop those things, but there's lots of opportunities for it. And we're starting to see technologies being introduced like silicon photonics that I showed you, and these future ideas of using photonics, of making very complex optics that we couldn't make before, sort out different shapes of light beams and the like, is very exciting. So one thing all us scientists and engineers have to do is we have to acknowledge people, end of talk, so we have to acknowledge the people who funded us, and we have to acknowledge all our collaborators. So let me just acknowledge, first of all, Andrew Carnegie, who, as Alan mentioned, did fund my graduate work, my postgraduate work at Heriot-Watt, and also a sabbatical I had recently, so thank you, Mr. Carnegie. Alexander Graham Bell. I worked for Bell Labs for 15 years in New Jersey, and that was he who paid for that, I think. You can see good pictures of him in the pub along at the end of the road here. They have pictures of him up on the wall. And then my collaborators, James Clerk Maxwell. Without him, I wouldn't be here. There's a great statue of him outside. Of course, one of the giants of physics, and his equations have held up. They just completely transformed our ability to work with light and all sorts of electromagnetism. And finally, I'll just give one more nod to William Thomson for being something that's really important and is sometimes missed. Somebody who is both a scientist and an engineer. And the Royal Society of Edinburgh and the Royal Academy of Engineering, they epitomize that idea. It's a really important idea, and I'll leave you with that. Thank you very much.
For opening your minds, I invite you to take a seat, and we have about 50 minutes or so for questions from the audience. I think David has opened our minds to things that are actually close to us, particularly the internet, which we all use these days. And I'm sure there's lots of questions. The way we're going to do this, there are two ladies at the side have roving microphones, so if you have a question, please raise your hand, wait for the mic coming. Please keep your question brief and to the point, and hold your mic close to your mouth so that we can hear you. So, who would like to kick off with a question? Yes, in the blue.
Hello, greatly enjoyed the talk. You've spoken a lot about limits and issues with information processing and bit processing, and I was curious to know to what extent advancements in quantum computing may help with resolving some of those issues.
Yes, the issue of quantum computing is a very interesting one. I think quantum computing is kind of like 1 to 2 breakthroughs away from us really being able to engineer a big system to do something. That doesn't mean we shouldn't look at it. And ironically, one of the things that some of this optics I've been talking about enables you to do is to play about with some of the ideas of quantum computing, because it enables you to make sort of arbitrary linear networks and so on. I think we're a ways out from quantum computing. It's a fascinating field. It's making us think about quantum mechanics in different ways. One of the things about optical communications is it uses an idea in quantum mechanics that is so bizarre, and it just uses it 250 trillion times a day, which is something called wave-particle duality. And it's the fact that the light going down these fibers is simultaneously a wave and a particle. Go figure, how can that be? We're just beginning to understand some of these ideas like entanglement. Entanglement's a very, very quantum mechanical idea that's deeply tied up with ideas of quantum computing. I think we're away from being able to implement those things, but it's great stuff to work with, and maybe someday these ideas of things like entanglement will become as routine as wave-particle duality is in optical networks. So it's a ways out, but it's a very interesting thing to look at.
Okay. Ian.
I'm a software guy, and so I'm looking for software solutions to this problem. And it seems to me that packet switching has been a very good, it's enabled the internet, but it's a bit like sending a letter in 1,000 pieces and having it sorted in 1,000 different sorting offices. Now, is there not a software solution to this? Could we not make these packets bigger, or or more connected or whatever. You know, all this switching seems to be what's taking all the load.
So the hardware people will always say that they're the people who allowed the software people to get progressively more inefficient over the years, right? And there's a thing called Gates's law. So I showed you Moore's law. Do you know Gates's law, which is that the number of transistors required to process a simple letter doubles every 2 years. The software guys have got a terribly, terribly hard job. I mean, just writing software that works is really hard. So for years, they've lent on the fact that the hardware was getting better every year. But we're sort of getting to the point where we have to stop doing that. And this is a very challenging thing. And it's, you know, you could write software where you counted the number of bit flips you had to do, right? And you could say, I'll make that a metric for the software. The problem is it's worse than that. As I said, the communication is the thing where the energy really is. How do you write software in some way in which the communication cost is built into a metric for you deciding what's a good algorithm, for example? And I think that's very difficult, but I think we're going to have to do everything. And I think we're going to have to figure out different ways of looking at software with different metrics for success. And I see that as a very basic software issue. And I really hope that the community sort of digs into that one, because we're going to have to do everything we can get our hands on to solve these problems.
Yes, in the white.
Yes, just to add to my thanks for a fantastic presentation. I guess you touched on doing the computations at a chip level, perhaps in an optical domain, and that gets rid of a lot of the issues you've got in terms of taking the electrons in there and pushing them around, etc. What I was not clear on, perhaps, was are you suggesting we could use an optical signal to modulate another optical signal? Because that seems to be the key to making the transistor an optical device, if you like.
Right, so there's a very good question, and in the 80s I got involved with these ideas of optical computers. We looked at them for a while, and Andy, who's sitting next to you, knows all about this. He can give you a lecture about it later on, maybe you already know about it. That was a very interesting research topic. One of the things that came out of that was that, well, maybe that's interesting, but silicon is a very difficult thing to compete with. You know, energy per logic operation is really, really hard to compete with, and the volume of transistors you can make is really hard to compete with. But copper is not so hard to compete with. And it was becoming clear towards the end of the 80s and into the 90s that really having optics compete with copper was a very good thing to look at, and that was perhaps more low-hanging fruit than trying to do the logic optically. And that is in fact what has happened. Of course, the long-distance network long since went that way. And it is, whether or not we come up with revolutionary technologies, the optics is progressively replacing copper further into machines in some sort of evolutionary fashion. Now, should we go all the way to optical logic? It's not clear that there's much benefit to that in the short term. It's a very hard thing to do. And to, you know, as I said, we're making chips now with literally 2 billion transistors on them. If not only would we have to come up with an optical logic device, but one that we could make 2 billion of for, you know, £3 or something, that's also very hard. And that's not the key to the problem for the foreseeable future. We're dealing with these interconnect problems. So we do need devices that are very efficient at going from the electronic into optical domain. And that's well worth focusing on. And I think that, you know, we're looking at devices now. We're getting devices that will run with less than a femtojoule in the lab. I can see us going down to 100 attojoules, and that would already be great, and we could build those into systems. Should we stop working on the optical logic? No, but you have to be very careful that you're really satisfying the criteria for logic. And there are lots of criteria, and a large number of the proposals out there for optical logic don't meet them. So that's tough, but once you get down, you could think once you get down to single photon level, which is a way out, but it's worthwhile thinking about those ideas. It's not going to be anything close in, but it is worthwhile thinking about those ideas as a research topic, but I don't see us replacing the transistors anytime soon.
Malcolm.
So I used to listen to RAEng Lecture.
You put me to shame there, David. But I'd like to ask you a question that I know you've already answered in another context somewhere.
Okay.
And that is there a biological answer to this problem? What if we look at the brain as a processing engine, based as it is in its own architecture and so on? Can we learn anything from that in solving these problems, or has the brain already been left well behind in the story?
I don't think the brain has been left well behind, and people who work in that area, there's lots of attempts to make sort of neural-inspired machines, and my understanding is that the concepts have worked at the small scale, but we're still kind of missing the big-scale concept that suddenly turns these billion transistors into a thinking being. I think we're missing that, but I'm not an expert in that. Is there something to be learned from biology? Of course there is, and architecturally there's a tremendous amount. It's an interesting question whether there's something physically to learn from it. One of the cute things about biological systems is they're actually very slow, and they do these phenomenal processing tasks, right? They don't send information around at high rates, and I don't know how they do it. So I think that's a very interesting question, but we need some sort of inspiration at the systems level to understand what we're doing, I think. And that, as my understanding, not being in the field, it was not something that's clear to us yet. Maybe somebody in the room here knows that better than I do.
So why doesn't the brain overheat without optical interconnect?
Well, you realize that the reason why we eat meat or have to eat a lot of vegetables is to keep the brain running, right? This is a 10 or 20 watt object. And the sloth only has to eat these leaves up in the trees because his brain doesn't work very fast. That's a biological, evolutionary niche trade-off. We have to eat all this food to keep the brain running, basically. So I think we're kind of food limited in how big our brains can be, or something like that, right? I mean, that's kind of what limits where we are.
Okay. Another question? Yes, in the middle.
Hi, I was just slightly appalled to learn how much energy we're dissipating by just doing a Google search, and I was wondering, especially in the context of global warming, and I sort of had thought of myself as being quite ecologically conscious and aware, like, is there anything we can do to limit the amount of energy that you're dissipating by using the internet?
Is there anything you can do to limit the amount of energy?
As a normal person, like changing your habits.
Don't use wireless connections, right? They are really high dissipation if you're really worried about it. I mean, it's not serious, but that would be one thing you would start to do. One thing I will say is that companies like Google are very well aware of this. And if you look at the engineering they've done on their servers, for example, there's a kind of load factor. I forget what the term for it is, but if you need to dissipate 100 watts in your chip, how many watts are you bringing into the building? And there's a factor there, and I know that Google has squeezed that way down. It used to be people run at 2 or 1.5 or something. I don't know the numbers, but my understanding is they've really squeezed that. So companies like Google are very well aware of this, just for the straight and dollar reasons, right? They're going to buy all this power, but they also know, I think, that it looks bad ecologically if they're not paying attention to this, and they do. They don't have a simple solution to it, but they would love to have a solution for all sorts of reasons. As to what you yourself can do, turn the computer off and then things like that are all good, and don't use your wireless connection if you really want to do it.
So is the US bearing the brunt of the environmental damage because much of this is located in the US via Google?
I don't really know the answer to that. I know that the various of these data centers are strategically located beside rivers and the like so they can run as efficiently as they can possibly run. And there is some argument that you might put all the data centers up somewhere above the Arctic Circle so that it was easier to cool them, but then that might melt the tundra, so maybe that's not such a good idea. Or maybe you put them out in space or something, I don't know, you can cool to a 3-degree background if you go out there. It's a good question. I don't think I know the answer to that one.
Do we have any? Yes.
I'm not an engineer. I'm just an ordinary member of the public with an interest. And if my question is a bit naive, I apologize. I was under the impression, or I have a simple idea, that when I use my cell phone, the information goes up to satellite and comes down in California. And I didn't realize that we were still using optics and fiber cables. Where do the satellites fall in this issue?
So we used to use satellites. There are two things wrong with satellites. One is it just took geostationary satellites. It takes too long for the electromagnetic waves to go up and back, and you don't like the delay. But the real reason is you can't get nearly enough bits per second down those connections. You're very limited the amount of bits per second you can send over radio waves compared to what you can send over light. So one beam of light has got the capacity to carry much more information. And the underlying reason for that you can think of in terms of the frequency of it. So radio waves have got a frequency of maybe 100 million cycles per second. And roughly speaking, the number of bits on-offs that you can send down that is sort of like that same frequency. There's some factors you can put in there. So for wireless, that's 100 million per second, right? Optics is running at 100 million cycles per second. So not 100 million cycles per second, 100 million cycles per second. And that means it can carry 1 million times more information. And that's the simple answer to your question. There are some details around about it, but that's the basic answer. And that's basically why we don't use satellites, even for data transmission, where you might not be bothered about, a half-second delay or something going up and back. We don't use them even for that, because we can't carry enough data up to the satellite and back. So the signal from your cell phone is going to a local cell tower. In the local cell tower or close to it, it's turned into a light beam being turned on and off going down a glass fiber. That's pretty much what happens. And it pretty much stays in the glass, goes in and out of some switching machines along the way a little bit, but it pretty much stays in the glass until it gets to California, to whoever you're calling out in California. And then the last kilometer or so, maybe it goes over the wireless again.
Okay, we could probably have one more question. No, I think you've answered everything, David, so perfectly. So I think we've all greatly appreciated the talk. You can see it on the face of the people out there, but I would like to ask Philip Greenish from the Royal Academy of Engineering to give a vote of thanks.
David, thank you very much indeed. Well, good evening, ladies and gentlemen. As you've heard, I'm Philip Greenish. I'm Chief Executive of the Royal Academy of Engineering. The first thing I have to do is to tender the apologies of my president, Professor Dame Anne Dowling, who very much hoped to be here tonight, but unfortunately she is unwell, so has been unable to join us for this absolutely fascinating evening. But secondly, before I thank David, I'd like to thank the Royal Society of Edinburgh for putting on this lecture. It's a great event in our joint calendars. I have to say I hugely look forward to coming here each year for this lecture. It provides a great excuse to come up to the land where great engineers are born. And we've seen and heard one tonight. 2015 is the UNESCO International Year of Light. So it's really relevant that we've had this lecture tonight. And it's been a real privilege, too, to listen to one of the world's leading experts in this particular field. I have to say, before tonight, one hears of the sort of things that David's been talking to us about, but I hadn't really twigged quite how important this is, nor had I quite twigged how close to the point where these sorts of technologies are needed if we're going to continue anything like the rate of development that we've seen over the last 10, 20, 30 or so years. I think some of the comparisons we've been told this evening are quite extraordinary. The 7 bits per second transmission rate down a transatlantic cable compared with the phenomenal amount of information flow that we see today, that is quite extraordinary. The amount of energy dissipated or generated and then dissipated in producing all this information and sending it around the world is also quite extraordinary. And David didn't talk about the amount of carbon that is generated into our atmosphere as a consequence of all that. But that, of course, is also a very serious issue that engineers need to be dealing with. And when we think of how we're dealing with the carbon generation, I don't think many of us would have connected that issue with the work of people like David to reduce the energy that is required to do all of this. So, ladies and gentlemen, this evening we've heard an absolutely brilliant lecture. It's had a lot of technical content sufficient to satisfy those who are of a technically inclined nature and of understanding, but presented in a way that all of us, even those who are not expert in the field, could understand. It's been interesting. It's really important. I think it's not what he's been talking to us tonight about is little understood, except now by us. We do understand it. And it was beautifully presented. So, David, on behalf of all of us, may I thank you very much indeed.